Everyone talks about Mars. It's on t-shirts, in Elon Musk's tweets, in sci-fi movies. Mars is a dangerous destination, but here's something nobody tells you. The moon, the one poets write about and lovers stare at, that thing would kill you faster than Mars ever could. Not in some abstract sense. In ways that are more brutal and more immediate than anything the red planet has planned for you. And here is a question. If you could choose any place in the Milky Way to explore with no danger whatsoever, where would it be? Comment down below. I'll pin the most creative answer. Now let's begin. First, let's just get our bearings here, because I think most of us carry a kind of casual familiarity with the moon that actually masks how extreme and alien it truly is. The moon is roughly 384,000 kilometers away from Earth. On a cosmic scale, that's nothing. That's practically next door. It takes light just over a second to travel that distance. A spacecraft can get there in roughly 3 days. This closeness is part of why humans landed there first, back in 1969, and it's part of why space agencies keep returning to it as a stepping stone for deeper exploration. But closed doesn't mean friendly, and the moon's proximity to Earth has absolutely nothing to do with how hospitable it is to human life. Let's start with something most people never think about. The moon has no atmosphere, not a thin one, not a barely there one, basically none. What it does have is something scientists call an exosphere, an almost impossibly thin layer of atoms that is so sparse the individual atoms almost never even collide with each other. For all practical purposes, the surface of the moon exists in the raw, open vacuum of space. Now stop and think about what that actually means for a moment. You step outside without a suit. You have roughly 15 seconds of useful consciousness. Not because you explode, that's a movie myth, but because the oxygen already in your bloodstream is the only oxygen your brain gets. Your blood starts to boil at body temperature because there's no atmospheric pressure to keep it liquid. Every fluid in your body, in your lungs, your sinuses, your tissues, begins to vaporize. You don't freeze instantly either, because in a vacuum, heat leaves the body incredibly slowly through radiation rather than conduction. But none of that matters much, because you're already unconscious in under 15 seconds and dead in under 2 minutes. That right there is the moon's first gift to unprotected humans. But here's the thing, you're not going to step outside without a suit. You're an astronaut, you've trained for years. You've got the best equipment humanity has ever built. Surely that protects you, right? Yes and no. Because the moon has a whole list of other problems, and some of them are subtle enough to sneak past even the best protection we currently have. Let's talk about temperature. Because the moon's temperature swings are so extreme they almost seem made up. During the lunar day, the surface temperature in direct sunlight reaches around 127 degrees Celsius. That's well above the boiling point of water, hot enough to cook things, hot enough to melt certain materials and fuse others. Then the lunar night falls, and remember, a single day on the moon lasts approximately 27 Earth days, so we're talking about almost 2 weeks of continuous, blazing, unfiltered sunlight, followed by almost 2 weeks of continuous, pitch-black darkness, and the temperature plummets to around negative 173 degrees Celsius. That's roughly negative 279 degrees Fahrenheit, colder than most of Antarctica by a factor that genuinely strains the imagination. That's a swing of 300 degrees Celsius between lunar day and lunar night. 300 degrees. On Earth, even our most extreme environments, the heart of the Sahara versus the depths of a Siberian winter, don't come close to that kind of range. Now compare that to Mars. Mars is cold, certainly. A typical surface temperature on the red planet averages around negative 60 degrees Celsius. In winter, at the poles, it can drop to around negative 125 degrees. But Mars has a day that's almost identical to Earth's, 24 hours and 40 minutes. It has a thin atmosphere, only about 1% of Earth's density, but that thin atmosphere still acts as a slight thermal buffer, helping moderate temperatures. Mars doesn't swing from scorching to frozen and back over the course of weeks. It's more manageable, and for astronaut equipment, for habitat design, for engineering anything that needs to function reliably, that matters enormously. Every material expands in heat and contracts in cold. When you're dealing with a 300-degree swing, every bolt, every seal, every circuit board has to be designed to survive a thermal cycle that nothing on Earth experiences. The engineering required to build a lunar habitat that survives those swings for months or years, safely, reliably, without catastrophic failure, is staggering. Mars gives you a fighting chance. The Moon in this category is essentially a design nightmare, but we're only just getting started. Because the temperature isn't even the most dangerous thing on the Moon, not by a long shot. We'll get into the real killer in a moment. But first, I want to plant a seed. The thing that truly makes the Moon so dangerous, the invisible threat that hangs over every single moment you spend there, is something you can't see, can't feel, and can't run from. And it's something that puts Mars's thin atmosphere into a whole new light. Stay with me, because this is where it gets truly fascinating and genuinely terrifying. Let's talk about radiation. And I don't mean the kind of radiation you think about when you picture a nuclear power plant, or those little yellow warning signs, or even an X-ray at the dentist's office. I'm talking about something far older, far more powerful, and far more relentless. Something that has been streaming across the universe since the first stars exploded billions of years ago. Something that, right now, as you sit here watching this video, is being blocked by Earth's magnetic field and atmosphere, two invisible shields that you have never once had to think about, and yet owe your existence to entirely. Take those shields away, and you get the Moon. Here's the basic picture. Out in space, there are two main sources of dangerous radiation that astronauts have to worry about. The first is the Sun. Our star is constantly releasing a stream of charged particles, mostly protons and electrons, called the solar wind. Most of the time, this is a relatively steady flow, like a cosmic river. But the Sun is also unpredictable. It erupts, it flares. Solar particle events, sudden, violent bursts of radiation from solar flares and coronal mass ejections, can spike radiation levels dramatically in a matter of hours. We're talking about doses that, without protection, could cause acute radiation sickness, nausea, vomiting, hair loss, immune system collapse. In extreme cases, death, the second source, is even more extraordinary. It comes not from the Sun, but from the universe itself. These are called galactic cosmic rays, and they are among the most energetic particles in existence. Born in the violent deaths of stars, supernovae, neutron star collisions, the ferocious environments around black holes. These particles travel across the galaxy at nearly the speed of light. They are essentially the nuclei of atoms, stripped of their electrons, moving so fast and carrying so much energy that they can punch straight through several centimeters of solid metal. They are nearly impossible to stop completely with conventional shielding. On Earth, you don't have to worry about any of this. Our planet has two layers of defense. The first is the magnetosphere, a vast invisible magnetic bubble generated by the churning of molten iron in Earth's core. This bubble deflects the solar wind and a significant portion of cosmic radiation before it ever reaches the upper atmosphere. The second layer is the atmosphere itself, roughly 10 metric tons of air above every square meter of the surface, acting as a physical barrier that absorbs and scatters incoming radiation particles. The result? On Earth's surface, you receive about 3 millisieverts of radiation per year from all natural sources combined. That's considered the baseline, the background noise of living on a planet with a magnetic field and an atmosphere. On the International Space Station, which orbits in low Earth orbit, still partially inside the protection of Earth's magnetosphere, astronauts receive about 80 times that, around 240 millisieverts per year. That's already enough that NASA carefully tracks every astronaut's cumulative lifetime dose and imposes career limits. Now step out of low Earth orbit, step away from Earth's magnetosphere entirely. Suddenly, you're in a completely different world. According to research from the European Space Agency, an astronaut on the lunar surface can be exposed to doses up to 700 times higher than on Earth. 700 times. That number is so large it almost loses meaning. So let me put it another way. One single day in space beyond Earth's protection can expose you to roughly the same amount of radiation you would normally absorb over an entire year on Earth's surface. Physicist Marco Duranti, who studies cosmic radiation, has put it bluntly: one day in space is equivalent to the radiation received on Earth for a whole year. And the Moon has no magnetic field worth mentioning. It has no real atmosphere. There is nothing between you and the full, unfiltered fury of the cosmos. Every solar flare, every galactic cosmic ray, every charged particle screaming across the solar system hits the lunar surface with essentially nothing in the way. This is not a minor inconvenience. This is an existential problem. The biological effects of this kind of radiation are serious, layered, and deeply unsettling. The most immediate concern is cancer. High-energy particles tear through your DNA like bullets through paper, breaking strands, causing mutations, scrambling the genetic code that your cells depend on to replicate correctly. The more exposure you accumulate, the higher your lifetime cancer risk climbs. But it doesn't stop there. Recent research, including NASA's famous twin study, which compared astronaut Scott Kelly, who spent nearly a year on the International Space Station, to his identical twin brother Mark Kelly, who stayed on Earth, showed that radiation exposure causes changes in gene expression, immune system disruption, and measurable DNA damage. And Scott was still in low Earth orbit, still benefiting from partial protection. The lunar surface is vastly harsher. There's also growing evidence from studies at particle accelerators, where scientists bombard biological cells with radiation designed to mimic the space environment, that cosmic rays can damage the brain itself, the central nervous system. Researchers have found signs of cognitive decline in animal models exposed to simulated galactic cosmic rays, memory problems, impaired decision-making, the kind of neurological effects that could compromise an astronaut's ability to function during a critical mission. And then there's the unpredictability of solar particle events. These storms can arrive with only hours of warning. If you're out on the lunar surface in a spacesuit when a major flare hits, you have very limited options. You need to get back inside a shielded habitat fast. But here's the twist. Even your habitat needs to be seriously reinforced to offer meaningful protection against the highest energy particles. Current spacecraft shielding materials absorb lower energy solar particles reasonably well, but the galactic cosmic rays, those heavy nuclei moving at near light speed, they laugh at aluminum walls. NASA's Artemis II mission, the first crewed flight to venture beyond Earth's magnetosphere since Apollo 17 in 1972, is preparing for this very carefully. The Orion spacecraft includes a designated storm shelter beneath the cabin floor, padded with stored equipment to provide extra shielding during a solar event. 2 radiation-sensing mannequins, nicknamed Helga and Zohar, flew on the uncrewed Artemis I test mission in 2022. One wore a protective vest developed by an Israeli company called STEMRAD. The data suggested the vest reduced radiation exposure from solar storms by roughly 40 to 60%. That sounds encouraging, but 40 to 60% of a potentially lethal dose is still a significant dose. And a vest doesn't do anything about galactic cosmic rays. Scientists writing in Science magazine in early 2026 Put it directly, radiation is the showstopper, the #1 limitation to how far and how long humans can safely explore deep space. It sits at the top of NASA's list of unsolved health challenges. And for the moon specifically, where there is no natural protection at all, it is the defining problem of any long-duration mission. Now, here's where Mars starts looking genuinely interesting. Mars also has no magnetic field. That's true. Its global magnetic field collapsed billions of years ago, and today the planet has only weak, patchy remnants of magnetism in certain regions of its crust. So Mars is not protected from space radiation in the way Earth is, but Mars does have something the Moon completely lacks: an atmosphere. Thin as it is, about 1% of Earth's atmospheric density, that layer of mostly carbon dioxide still does something remarkable. It stops certain particles, it slows others. It causes incoming radiation to interact and fragment before reaching the surface. The result is that the radiation environment on the Martian surface, while still significantly higher than on Earth, is meaningfully less severe than on the open lunar surface. Data from NASA's Curiosity rover, which has been trundling across the Martian surface since 2012, confirm this directly with its onboard radiation assessment detector instrument. Measurements showed that the Martian surface receives roughly 233 millisieverts of radiation per year, which is still serious, still well above Earth's baseline, but dramatically lower than what you'd face standing unprotected on the Moon. Think about what that means architecturally and for mission planning. On Mars, a relatively modest habitat with some additional shielding, perhaps a layer of Martian soil piled on top, which engineers have already explored as a concept, can bring radiation levels down to ranges that might be manageable for long-duration human occupation. The atmosphere provides the first layer of protection. Habitat design provides the second. On the Moon, you're starting from zero. Every particle that hits you has had nothing in its way. You have to provide all the shielding yourself from scratch, using materials you've either brought from Earth or manufactured on site. And for the worst offenders, the galactic cosmic rays, we currently have no shielding solution that's both effective and light enough to be practical for spaceflight. There's another factor that makes the radiation picture on the Moon particularly brutal, and it's one that catches a lot of people by surprise. The Moon's surface itself becomes a source of secondary radiation. When high-energy particles slam into the lunar soil, they don't just stop. They trigger cascades of secondary particles, neutrons and gamma rays, that scatter in all directions, including upward. So you're not just getting hit from above by the direct radiation coming from space. You're also getting hit from below, from the sides, from radiation bouncing off the ground beneath your feet. The Chang'e 4 mission, China's lunar lander that touched down on the far side of the Moon in 2019, carried an instrument called the Lunar Lander Neutron and Dosimetry Experiment that has been measuring this effect directly. The data confirmed that the lunar surface radiation environment is significantly more complex and more dangerous than simply shielding from above would suggest. The Moon bombards you from every direction. Now, I want to take a moment here because we're deep in the science, and I don't want the weight of all this data to obscure the truly breathtaking thing that's happening underneath all of it. Think about what we're actually talking about. The atoms in your body, the carbon in your DNA, the iron in your blood, the calcium in your bones, were forged inside stars that lived and died billions of years before our solar system existed. You are, in the most literal and scientific sense, made of stardust, and the radiation streaming across the cosmos right now, that's also the legacy of those same stars, the shock waves from their deaths, the particles flung outward when they exploded in supernovae so powerful they could briefly outshine entire galaxies. We are the universe becoming aware of itself. And when we try to step out into that universe, when we try to visit the moon or journey to Mars, we run headlong into the raw, unfiltered energy of the cosmos that made us. There's something almost poetic about that. Something that should fill us with awe, even as it humbles us. But the cosmos doesn't care about poetry. And the moon's radiation environment is genuinely one of the hardest problems standing between us and a sustained human presence in deep space. So we've talked about the vacuum, the temperature extremes, the radiation, and we're not done yet, because there's another hazard on the moon that is so strange, so counterintuitive, so unlike anything we face on Earth, that when astronauts first encountered it during the Apollo missions, it completely caught them off guard. It's dust, not ordinary dust, not the kind you wipe off your bookshelf. Something far stranger, something that behaves almost like a living thing, clinging to everything, invading everything, potentially lodging inside human lungs and staying there forever. The story of lunar dust is one of the weirdest and most underappreciated chapters in the history of space exploration. And it's a hazard that Mars once again handles very differently. That's where we're heading next. Let's talk about dust. And I know what you're thinking. Dust? Really? Out of everything we've covered so far, the vacuum, the temperature swings wild enough to warp metal, the invisible radiation pouring in from dying stars. You're going to tell me that dust is the thing that keeps engineers up at night? Yes, exactly that. Because lunar dust is not like any dust you have ever encountered. It is not like the fine powder that settles on furniture, or the grit that blows across a desert, or even the volcanic ash that drifts down after an eruption. Those materials have all been shaped by forces that soften and round them over time. Wind, water, friction, the constant tumbling of particles against each other through billions of years of geological activity. Earth's dust has had its edges worn away. It's been weathered. Lunar dust has not. The moon has no wind, no water, no rain, no rivers, no ocean waves, no weathering of any kind in the way we understand it on Earth. What the lunar surface does have is billions of years of constant bombardment from above, micrometeorites, cosmic rays, and the relentless stream of charged particles from the solar wind, all smashing into the surface, grinding the rock down into finer and finer fragments, and then doing something truly strange to those fragments at the microscopic level. Under an electron microscope, lunar dust grains look almost menacing. They are jagged, angular, glassy. Many of them are partially melted, fused into irregular shapes by the heat of micrometeorite impacts. Some are hollow spheres of volcanic glass from ancient eruptions billions of years old. Some have razor-sharp edges, so fine they make industrial cutting surfaces look blunt. And because there's no atmosphere to create electrostatic equilibrium the way Earth's does, these particles carry powerful electrostatic charges. They cling to absolutely everything they touch with a tenacity that borders on aggressive. The Apollo astronauts discovered this the hard way. Buzz Aldrin described it as one of the most persistent and annoying problems of the entire mission. Neil Armstrong noted that dust coated everything within minutes of the first moonwalk. By the time the astronauts climbed back into the lunar module after their surface excursions, their suits were visibly darkened by a thick coating of fine grey powder. They tried brushing it off. It didn't work. The dust clung to the suits, to the gloves, to the equipment, to the helmet visors. It scratched the outer layers of the visors. Those scratches permanently reduced visibility. It worked its way into the joints of the suits, grinding against the mechanisms with every movement, degrading the suit's ability to flex and seal. Apollo 12 astronaut Pete Conrad compared the abrasiveness of lunar dust to fine sandpaper that never goes away. And then there was the smell. When the astronauts finished their moonwalks and repressurized the lunar module, some of the dust inevitably came inside with them. Harrison Schmitt, the only professional geologist to walk on the moon, during Apollo 17 in 1972, almost immediately experienced a reaction. His eyes watered, his sinuses became congested. He described the smell of the disturbed lunar dust as something like gunpowder or spent fireworks. Several other Apollo astronauts reported similar reactions. What they were experiencing was their respiratory systems encountering the sharp, reactive, chemically fresh surfaces of lunar particles, surfaces that, because they had never been exposed to oxygen or water vapor, were essentially primed to react with the first biological tissues they came into contact with. This is where lunar dust stops being a nuisance and becomes a genuine medical threat. Here's the core problem. Particle size matters enormously when it comes to lung damage. Particles larger than about 10 micrometers, 10 millionths of a meter, are generally caught by the nose and upper respiratory tract. They get filtered out or coughed up. Particles between 2.5 and 10 micrometers make it deeper into the airways. But particles smaller than 2.5 micrometers, what scientists call fine particulate matter, penetrate all the way into the deepest regions of the lung, the tiny air sacs called alveoli, where oxygen exchange happens. And at that depth, the body's ability to clear particles is dramatically reduced. Lunar dust has particles across all of these size ranges. A significant fraction falls into that deepest, most dangerous category. And unlike the rounded, relatively inert particles of terrestrial dust, lunar particles are jagged, reactive, and coated in chemically active compounds, including nanophase iron, agglutinates, and glassy materials that are particularly good at generating free radicals when they interact with biological fluids. Free radicals are unstable molecules that damage cells. They tear apart DNA, they trigger inflammation. Long-term exposure to fine silicate dust, which is chemically similar in some ways to lunar regolith, is already known to cause serious lung diseases, silicosis, chronic inflammation, fibrosis, scarring of lung tissue that permanently reduces lung function and cannot be reversed. Black lung disease in coal miners operates on similar principles. NASA researchers have been running experiments to understand what lunar dust would actually do to human lungs with extended exposure. Laboratory studies using simulated lunar regolith, materials designed to mimic the physical and chemical properties of actual moon soil, have shown that even low concentrations can cause measurable cell death and DNA damage in lung tissue cultures. A study published in the journal GeoHealth in 2018 found that simulated lunar dust was cytotoxic, meaning it killed cells, at levels significantly lower than what astronauts might actually be exposed to during extended surface operations. And here's the deeply uncomfortable part of all this. We've never had a human being spend more than about 3 days on the lunar surface. The longest any Apollo crew spent on the moon was Apollo 17, which lasted just under 75 hours of total surface time spread across 3 moonwalks. In that short window, dust was already causing suit degradation, equipment problems, and respiratory irritation. What would 6 months of daily lunar surface operations do to a human respiratory system? Honestly, nobody knows. We don't have the data because no human has ever experienced it. But the laboratory evidence is not reassuring. There's another layer to the dust problem that speaks directly to engineering and long-term mission survival. Lunar dust doesn't just attack human bodies, it attacks machines. During the Apollo missions, dust infiltrated the spacesuit's joints and bearings, increasing the force required to move the suit and causing premature wear. It coated the solar panels on the various surface instruments left behind by the astronauts, reducing their power output. On the robotic side, NASA's lunar rovers deployed as part of later missions accumulated dust on their solar panels so quickly that dust management became a primary operational concern. The Lunar Reconnaissance Orbiter, which has been orbiting the Moon since 2009, carries dust detection instruments, partly because understanding dust behavior is considered so critical for future surface operations. Lunar dust is also electrostatically levitated because the Moon's surface is constantly being bombarded by the solar wind and ultraviolet radiation. It builds up electrostatic charges, particularly at the boundary between the sunlit and shadowed regions. This charge differential causes fine dust particles to actually lift off the surface and float, sometimes to heights of several meters, sometimes much higher. Astronauts on the later Apollo missions reported seeing a strange glow along the lunar horizon just before lunar sunrise, which scientists now believe was caused by vast clouds of electrostatically levitated dust scattering sunlight above the surface. This means that even without physically walking across the surface, lunar dust can find its way to equipment, solar panels, and suit exterior surfaces purely through electrostatic attraction. You can't simply seal a habitat and call the problem solved. The dust will find a way in, on every entry and exit, on every spacesuit surface, through every airlock cycle. Managing contamination becomes a constant, never-ending operational challenge that consumes time, energy, and resources on every single day of a lunar mission. So what does Mars offer by comparison? Well, Mars has dust too. Nobody is pretending otherwise. Martian dust storms are legendary. The planet experiences regional storms fairly regularly, and roughly every few Martian years, a global dust storm erupts that can blanket the entire planet for weeks or even months. These storms are so powerful that in 2018, one of them ended the mission of NASA's Opportunity rover, which had been operating brilliantly for nearly 15 years, by blocking enough sunlight to starve its solar panels of power. But Martian dust, for all its dramatic scale, is fundamentally different in character from lunar dust. Martian particles have been shaped by billions of years of wind. They have been carried and tumbled and rounded against each other across vast distances. They are finer in some ways, yes, but they are also less angular, less glassy, less chemically reactive. They have interacted with small amounts of water ice in the ancient past and with the thin atmosphere in the present, which has altered their surface chemistry compared to raw, freshly shattered lunar regolith. The health risks from Martian dust are still real and still being actively researched. Perchlorate compounds, chlorine-containing salts, have been detected in Martian soil, and perchlorates are toxic to the human thyroid gland if inhaled or ingested in sufficient quantities. That's a genuine concern for any future Mars colonists. But perchlorates are water-soluble and can potentially be managed through filtration and decontamination procedures in ways that the physical damage from jagged lunar silicates cannot. And critically, Mars's thin atmosphere, while it creates dust storms, also keeps the finest particles airborne and distributes them more evenly. The electrostatic levitation problem that plagues the Moon is far less severe on Mars, partly because Mars does have that thin atmospheric buffer, and partly because the surface charging dynamics are different. Getting in and out of a Mars habitat would still require dust management protocols, but the suit degradation, the respiratory risks from jagged particles, and the equipment contamination picture all look meaningfully more manageable on Mars than on the Moon. None of this means Mars is easy. I want to be very clear about that. Every single thing we've discussed about the Moon, the radiation, the temperature swings, the dust, Mars has a version of, but in almost every category, Mars's version is less extreme, more manageable, or at least more addressable with technology we can realistically imagine building. The Moon's version is, in multiple categories, right at or beyond the edge of what our current engineering and medical knowledge can handle safely for long-duration missions. And we haven't even talked about what the Moon does to the human body beyond the lungs. Because here's something that doesn't get nearly enough attention in the popular conversation about space exploration. The human body is extraordinarily well adapted to living on Earth. It evolved here. Every system, skeletal, muscular, cardiovascular, neurological, immune, was shaped by roughly the same gravitational pull for our entire evolutionary history. 1g, always 1g. The Moon's surface gravity is about 1/6 of Earth's. Mars's is about 38% of Earth's. Both are less than what our bodies need, but they are not equally bad. Long-duration spaceflight in microgravity, the essentially weightless environment of orbital flight, causes a cascade of physiological problems that NASA has spent decades documenting and trying to address. Bone density decreases, muscles atrophy, the spine lengthens as the discs decompress, fluid shifts from the lower body toward the head, increasing intracranial pressure. Vision problems caused by this fluid shift, a condition called spaceflight-associated neuroocular syndrome, or SANS, have been found in a significant proportion of astronauts after long missions. The cardiovascular system, no longer fighting gravity to pump blood, becomes deconditioned. Now, both the Moon and Mars provide some gravity, which is better than the near-zero gravity of orbital spaceflight. Exercise protocols that help on the ISS would also help on the lunar and Martian surfaces, but 1/6 of a G is not very much. It's probably not enough to fully prevent the bone density and muscle mass losses that occur in low-gravity environments. 38% of a G. Mars's gravity is still low, but it's more than 6 times stronger than the Moon's pull. It would load the skeleton, the muscles, and the cardiovascular system more effectively. Over a year-long Mars mission, this difference in gravitational loading could have significant effects on long-term health. Over a permanent settlement, if we're talking about people who might live their entire lives on another world, the divergence between 1/6 G and 38% G becomes enormous. Children born and raised on the Moon would develop skeletons, muscles, and cardiovascular systems shaped by 1/6 of Earth's gravity. Whether such a body could even return to Earth and survive is an open and deeply serious question. Children born on Mars would face similar challenges, but to a lesser degree. We are organisms fine-tuned for 1G. Every fraction of a percentage point of gravitational acceleration matters for long-term human health, and the Moon gives you so much less of it. Let's talk about your mind. Because here's something that gets overlooked almost every time the conversation turns to space exploration. We spend enormous amounts of time and energy thinking about what the vacuum does to the human body, what radiation does to DNA, what dust does to lungs and machinery. All of that is critically important. But the human brain, the thing that makes you you, the thing that processes experience and makes decisions and holds everything together under pressure, is also going on that journey. And the environment it finds itself in matters just as much as the environment your body is exposed to. Space is psychologically brutal in ways that are only beginning to be fully understood. Start with isolation. Human beings are, at the deepest level of our evolutionary history, social animals. We lived in groups for millions of years. Our brains are wired for connection, for reading facial expressions, for hearing familiar voices, for the subtle, constant background hum of being near other people. Solitary confinement is considered a form of torture in most of the world precisely because extended social isolation causes measurable psychological and even neurological damage. Anxiety, depression, cognitive decline, hallucinations in extreme cases. Now, space missions are not solitary confinement. Astronauts travel in crews and communication with Earth is maintained, but they are isolated in a profound and very specific way. You are cut off from the vast majority of your social world, your family, your friends, the casual human interactions that make up the texture of everyday life, a conversation with a stranger, a crowded cafe, the background noise of a city. all of that disappears. You are sealed inside a small, artificially maintained environment with the same small group of people day after day for months or potentially years. The psychological research on this is extensive. NASA has studied it through analog environments, isolated research stations in Antarctica, underwater habitats, sealed simulation facilities. The consistent findings paint a complex picture. In the early weeks of an isolated mission, crew members tend to be energized, motivated, focused on the novelty and excitement of the experience. But somewhere around the midpoint, a phenomenon researchers call the third quarter effect. Morale tends to dip, tension between crew members increases, irritability rises. Minor interpersonal conflicts that would be trivial in normal life can become significant in a confined environment where there is literally nowhere else to go. By the final stretch of a mission, performance and morale can improve again as crew members focus on the end goal. But the psychological strain of the middle period is real, consistent, and well documented. And this was all studied for missions measured in weeks to months. We are now contemplating missions to Mars that would last somewhere between 1.5 and 3 years for a single crewed round trip, depending on the trajectory. Permanent settlements would involve people who might never return to Earth at all. The psychological demands of that kind of commitment are genuinely unprecedented in human history. Yes, sailors once crossed oceans for months at a time. Yes, Antarctic expeditions have lasted through entire polar winters, but those people could at least look out a window and see a sky, feel wind on their faces, watch seasons change. They were isolated from civilization, but not from the natural world. In space or on the surface of an airless world, nature itself becomes the enemy. There is no sky to look at without a visor filtering out lethal radiation. There is no wind that doesn't carry abrasive dust or represent a pressure breach risk. There is no step outside that doesn't require a full spacesuit donning procedure, taking 30 minutes to an hour. Now here's where the Moon and Mars diverge in a psychologically fascinating way. And it's a divergence that almost nobody talks about. The Moon is close, at its average distance of 384,000 kilometers from Earth. The Moon is close enough that communication signals travel between the two worlds, with a delay of only about 1.3 seconds one way, 2.6 seconds round trip. That is fast enough for real-time conversation. You could call your family on the Moon and have something approaching a normal phone call with a barely noticeable delay. You can also see Earth from the Moon, not just as a distant dot of light, but as a vivid, gorgeous blue and white sphere filling a significant portion of the lunar sky. The Apollo astronauts spoke about this with a kind of reverence that never quite left them. Edgar Mitchell, Apollo 14 astronaut, described looking back at Earth from space as a sudden, overwhelming realization of connectedness, what he later called a flash of understanding about the unity of everything. Dave Scott of Apollo 15 described Earth from the Moon as so beautiful it was almost painful to look at. The famous Earthrise photograph taken by William Anders during Apollo 8 in 1968 is considered one of the most influential images ever taken. It showed humanity, for the first time, what our planet looks like from another world, a fragile blue bubble hanging in black space. And it helped ignite the modern environmental movement. Earth, seen from the Moon, would be a constant companion, a psychological anchor, a visual reminder of everything you left behind and everything you're working toward. Mars doesn't have that. At its closest approach to Earth, Mars is roughly 55 million kilometers away, at its most distant nearly 400 million kilometers. The average distance across a typical mission is somewhere around 225 million kilometers. At those distances, communication signals traveling at the speed of light take anywhere from 3 minutes to 22 minutes one way. 6 minutes to 44 minutes round trip. That means a real-time conversation with Earth is impossible from Mars. You send a message, you wait, you get a reply, you wait again. In an emergency, a medical crisis, a critical equipment failure, a situation where you desperately need guidance from mission control, you are fundamentally on your own. Whatever expertise, whatever problem-solving capability, whatever wisdom is needed to survive that emergency has to already exist within your small crew. Earth cannot help you in real time. This is not just a communication inconvenience. It is a profound psychological and operational reality. On the Moon, mission control can watch every data feed in real time and bark urgent instructions the moment something looks wrong. On Mars, by the time mission control even knows something has gone wrong, the situation may already be resolved, for better or worse. And from Mars's surface, Earth is just a star, a bright one perhaps, to the naked eye, but a point of light indistinguishable from the thousands of other points of light in the Martian night sky. There is no vivid blue globe to remind you of home. There is no visual anchor. There is just the dark. The psychological literature on communication delay in isolated environments suggests this makes an enormous difference. Crew members on simulated Mars missions who experienced even modest artificial communication delays with their support teams reported increased feelings of autonomy, but also increased anxiety, decreased sense of safety, and greater reliance on internal crew dynamics, for better or worse. When crew dynamics go well, the team becomes more tightly bonded and self-sufficient. When they go poorly, with no quick outside intervention possible, interpersonal conflicts can escalate in ways that mission control back on Earth can do almost nothing about in real time. There's also the question of what researchers call Earth out of view psychology. Preliminary research, drawing on analog studies and interviews with long-duration ISS astronauts, suggests that the inability to see Earth from the surface of Mars could create a qualitatively different psychological experience than anything humans have faced before. Not just homesickness, not just isolation, something more fundamental, a sense of existential disconnection from everything familiar. Some researchers believe this could be mitigated by virtual reality environments, by carefully curated media libraries, by mission architecture designed to give crew members genuine autonomy and purpose. Others are less certain. The truth is, we simply do not know how the human psyche will respond to spending years on a world where Earth is invisible, and communication with loved ones requires a delay of up to 44 minutes round trip. No human being has ever experienced that. The closest analogue we have is the Apollo astronauts who passed behind the Moon and lost all contact with Earth for about 45 to 48 minutes at a time during lunar orbit. Several of them described those minutes of radio silence as among the most quietly powerful experiences of the entire mission, a sense of utter, complete isolation, unlike anything else. 45 minutes. Imagine 44 minutes every single time you tried to have a conversation with anyone you loved for 3 years. That said, there's a counter-argument worth taking seriously. Some researchers and explorers argue that the psychological burden of radical autonomy and distance might actually be freeing in ways that are hard to anticipate. The Apollo astronauts didn't just survive their missions psychologically. Many of them described the experience as the most profound and transformative of their lives. The overview effect, that shift in perspective that comes from seeing Earth from space, has been reported consistently across nationalities, backgrounds, and personality types. There is something about genuine distance from the familiar that can, under the right conditions, produce not despair but clarity. Whether that holds over years rather than days is the open question. And then there's something else. Something that cuts in a different direction for the Moon specifically. The Moon is tidally locked to Earth, meaning the same face always points toward us. If you're on the near side of the moon, which is where the Apollo missions landed, and where the most accessible resources tend to be concentrated near the poles, you always have Earth in the sky. But if you're on the far side of the moon, the side that never faces Earth, you have the opposite problem: no Earth in the sky, ever. And because the moon is so close, line-of-sight communication with Earth from the far side is impossible without relay satellites. China's Chang'e 4 mission needed a dedicated relay satellite called Kekiao, Chinese for Magpie Bridge, just to maintain communication with its far side lander. Any crewed base on the far side of the moon would face a version of the same challenge, compounded enormously by human psychological needs. This geographic split on the moon creates two very different psychological environments. The near side, with its constant view of Earth, might actually be psychologically easier than Mars, despite the greater physical dangers. The far side would offer the scientific advantage of being shielded from Earth's radio noise, a dream for radio astronomers, but would present psychological challenges that rival or exceed those of a Mars mission. Now step back from all the technical details for a moment and feel what this is really pointing at. We are a species that evolved for one world. Our bodies, our minds, our social structures, our deepest psychological needs, all of it was shaped by the specific conditions of Earth over millions of years of evolution. And yet here we are, seriously planning to send people to other worlds, permanently, raising children there, building civilizations there. The audacity of that is breathtaking. The ambition of it should fill you with awe, but it also means we have to be honest about the challenges. Not to say it can't be done. Of course it can eventually, with the right technology and the right preparation and the right understanding of what human beings actually need to survive and thrive away from home. But to do it right, we have to look clearly at what we're actually asking of the humans who will go, the physical demands, the psychological demands, the sheer, relentless difficulty of living in an environment that is indifferent to your existence in a way that no ecosystem on Earth quite matches. And when you do that honest assessment, when you lay the Moon and Mars side by side and ask which one is actually more survivable for long-duration human presence, the answer is more nuanced and more surprising than most people expect. The Moon has proximity. It has that gorgeous view of Earth. It has relatively easy communication. It could serve as a proving ground, a stepping stone, a place to develop and test the technologies and techniques we'll need for the longer journey to Mars. But its radiation environment is brutal. Its temperature swings are extreme. Its dust is medically dangerous and mechanically destructive. Its gravity is barely enough to matter. And if anything goes wrong, a suit breach, an equipment failure, a medical emergency, help from Earth, while faster than from Mars, still takes days to physically arrive. You can't be evacuated in a phone call. You can't be rescued by express delivery. The Moon will absolutely kill you if you're not extraordinarily careful, more easily and in more ways than most people think. And Mars? Mars is a harder journey, a longer stay, a more total commitment. In some ways, psychologically, it might be the more demanding choice. But the evidence, radiation measurements, atmospheric modeling, dust chemistry analysis, gravity calculations, suggests that for a permanent human presence, for civilization rather than just visitation, Mars actually offers a more forgiving starting point, which raises a question that has been building quietly underneath everything we've discussed so far. If the Moon is so dangerous, why are we going back? And the answer to that question leads us somewhere completely unexpected. Somewhere that reveals the Moon not as a dead end, but as potentially one of the most important places in the entire solar system for the long-term future of humanity. It involves water ice. It involves the bizarre physics of permanently shadowed craters near the lunar poles. It involves a resource so valuable in space that engineers refer to it as the oil of the solar system, and it involves a vision for what the moon could be, not a destination in itself, but the key that unlocks everything else. That's coming up now. Let's talk about shadow, not metaphorical shadow, not the shadow of danger or the shadow of uncertainty, though we've covered plenty of both. Literal shadow, permanent, ancient, billions of years old shadow sitting at the bottom of craters near the moon's north and south poles, craters so deep and the moon's axial tilt so slight that the sunlight has never once reached their floors in the entire history of the solar system. Not once, in 4.5 billion years. The moon tilts on its axis by only about 1.5 degrees relative to its orbit around the sun. Earth tilts at 23.5 degrees. That's what gives us our seasons, the reason summer days are long and winter days are short. The moon's near-zero tilt means its poles receive sunlight at an almost perfectly horizontal angle, skimming across the surface rather than pouring down into it. And in the deep craters clustered near the poles, some of them dozens of kilometers wide and several kilometers deep, the sunlight simply never reaches the bottom. The crater walls are too high. The angle is too shallow. Perpetual darkness fills those floors as absolutely as if they were sealed vaults. And in that darkness, at temperatures that plunge to around -240 degrees Celsius, making them among the coldest confirmed places in the entire solar system, colder than the surface of Pluto, something extraordinary has been accumulating: water ice. Water delivered to the moon over billions of years by comets and asteroids and water-rich meteorites that slammed into the lunar surface. Water that, when it hit the sunlit regions of the moon, immediately vaporized and drifted away into space. Because without an atmosphere, there's nothing to hold it. But some of that vapor, drifting across the surface, eventually migrated toward the poles. And at the poles, some of it found its way into those permanently shadowed craters where the temperatures are so cold that even water in a vacuum cannot evaporate. It simply froze and stayed, and accumulated over geological timescales into deposits that scientists now believe could hold hundreds of millions of metric tons of water ice. Perhaps more. The evidence for this has been building for decades. In 1994, the Clementine spacecraft detected what looked like signs of ice in permanently shadowed regions near the lunar south pole. In 1998, the Lunar Prospector mission found elevated hydrogen concentrations near both poles, hydrogen being a key indicator of water. In 2009, NASA deliberately crashed a spent rocket stage, the upper stage of the Atlas V rocket that had carried the Lunar Reconnaissance Orbiter to the Moon, into a permanently shadowed crater called Cabeus near the South Pole, and a following spacecraft called L-Cross flew through the debris plume and measured what came up: water, definitively, confirmed. The plume contained water ice and water vapor in concentrations that were genuinely exciting to the scientists analyzing the data. Since then, the Lunar Reconnaissance Orbiter has been mapping the polar regions in extraordinary detail. India's Chandrayaan-1 mission detected water molecules on the lunar surface. NASA's SOFIA Airborne Observatory, an infrared telescope mounted in a modified Boeing 747, detected water molecules in sunlit regions of the lunar surface as well, not just in the shadows, suggesting that water might be more widely distributed across the moon than previously thought, possibly trapped in tiny glass beads in the soil created by micrometeorite impacts. And in 2020, a remarkable set of studies published in Nature Astronomy significantly upgraded the scientific community's estimate of the total amount of water ice potentially locked in those permanently shadowed regions. The picture that emerged was of a moon that is considerably wetter than the bone-dry desert world most people imagine. Now, why does this matter so much? Water in space is not just water. It is everything. Think about what water actually is. It's hydrogen and oxygen bonded together, two of the most useful molecules in the entire toolkit of space exploration. Split water through electrolysis, run an electric current through it, and you separate it into hydrogen gas and oxygen gas. Oxygen to breathe. Hydrogen and oxygen together as rocket propellant, specifically liquid hydrogen and liquid oxygen, which is the most energetically efficient chemical rocket fuel combination known, and the same propellant used by the main engines of the space shuttle and the core stage of NASA's Space Launch System that powered the Artemis missions. Water to drink, oxygen to breathe, rocket fuel to go places. All three of those things, the three most fundamental resources for sustained human presence in space, can in principle be derived from water. And the Moon might have vast reserves of it sitting in those polar craters waiting. This is the concept that engineers and mission planners call in situ resource utilization, or ISRU. The idea is simple but transformative. Instead of bringing everything you need from Earth, which is extraordinarily expensive, because every kilogram you launch from Earth's surface requires enormous amounts of rocket fuel just to escape gravity, you use resources that already exist at your destination. And here's the number that makes ISRU so compelling. Reaching low Earth orbit from Earth's surface requires overcoming roughly 8 kilometers per second of velocity change, what engineers call delta V. Getting from low Earth orbit to the lunar surface requires roughly another 6 kilometers per second. The Moon's surface gravity is 1/6 of Earth's, and crucially, it has no atmosphere to fight through. Launching from the Moon, putting something into lunar orbit or sending it on a trajectory toward deep space, requires only about 2 kilometers per second of delta V, 2 kilometers per second versus 8. Launching from the Moon is dramatically cheaper in terms of propellant than launching from Earth. If you could manufacture rocket fuel on the Moon, using locally sourced water ice, split into hydrogen and oxygen by solar power generated on the sunlit crater rims just above those permanently shadowed floors, you could in principle create a refueling depot in space, a gas station sitting at the edge of Earth's gravity well. Spacecraft could launch from Earth carrying minimal propellant, refuel at the lunar depot, and then continue onward to Mars, the asteroid belt, the outer solar system, anywhere, with a fraction of the propellant budget they would otherwise need. This concept, sometimes called a cislunar propellant depot, has gone from a theoretical idea to a serious focus of NASA planning and private sector investment in just the last several years. Companies like United Launch Alliance have proposed architectures built around exactly this model. NASA's Artemis program, which returned humans to the vicinity of the Moon with Artemis 1 in 2022 and Artemis 2, the first crewed flight beyond Earth's magnetosphere since Apollo, is explicitly designed with resource utilization in mind as a long-term goal. The Artemis program's stated objective is not simply to plant a flag and leave, the way Apollo did. It is to establish a sustained human presence near the Moon, including a small orbital station called the Lunar Gateway, and develop the technologies needed to extract and use lunar resources. The south pole of the Moon, with its confirmed water ice and its nearby permanently sunlit ridges that could power solar arrays around the clock, is the primary target. Exactly where the ice is, how accessible it is, how pure it is, how efficiently it can be extracted. These are all open questions that require boots on the ground, or at least robots on the ground, to answer properly. But the potential is extraordinary, and there's more to the permanently shadowed regions than just water. Scientists analyzing data from the Lunar Reconnaissance Orbiter and other sources have found evidence that those cold, dark crater floors may contain a rich mixture of volatile compounds beyond water. Carbon dioxide, ammonia, methane, and other carbon and nitrogen-bearing molecules, all frozen and preserved in what are essentially natural deep-freeze storage vaults. These compounds are the raw materials of chemistry: carbon, nitrogen, hydrogen, oxygen, the four most important elements for life and for industrial processes, sitting together in the coldest, darkest corners of our nearest neighbor in space. Step back and let the full picture settle in for a moment. Here we have a world that we spent the last 4 parts of this video describing as one of the most hostile environments a human being could possibly inhabit. Lethal radiation, bone-cracking temperature extremes, medically dangerous dust, negligible gravity, and yet, tucked away in the permanent shadows at its poles, possibly waiting to be unlocked by a combination of solar power and electrolysis, are resources that could make the moon not just survivable, but strategically indispensable to the entire future of human civilization in space. The moon is not a dead end. It might be the most important piece of real estate in the solar system, not because of what it is to live on, but because of what it offers as a platform. This is the vision that the most ambitious space thinkers have been articulating for years. Build the infrastructure on the moon, develop the resource extraction technology, figure out how to keep people alive in that brutal environment for extended periods, not because the moon is the ideal place for a permanent human civilization, but because it's close enough to Earth to practice, close enough to rescue, close enough to iterate and fail safely. Use the moon as the proving ground, the testing laboratory, the propellant depot, and then, armed with everything learned there, make the push to Mars. Some people in the space community argue this is exactly backwards, that the moon is so different from Mars in its environment that what you learn on the moon doesn't necessarily prepare you for Mars, that the resources and technology you develop for the lunar environment won't straightforwardly transfer to a Martian context, that going to the moon first adds time and cost to a Mars program rather than accelerating it. Elon Musk, who leads SpaceX, has been openly skeptical of the moon-first approach, arguing that it's a distraction from the ultimate goal of making humanity multiplanetary by establishing a self-sustaining city on Mars. His vision centers on the Starship vehicle, a fully reusable, massive launch system designed to transport 100 or more people to Mars on a single flight. And the idea of moving so fast and launching so many missions that the sheer volume of activity accelerates the learning curve. NASA, the European Space Agency, JAXA, the Japan Aerospace Exploration Agency, and a growing coalition of international partners have staked out a more measured approach, centered on Artemis and the Lunar Gateway, using the moon as a waypoint. Both visions are serious. Both are being actively funded and developed. They represent a genuine philosophical and strategic debate about the best path forward for humanity in space, a debate that is happening right now, in real time, among real engineers, scientists, astronauts, and policymakers. And here's what makes this debate so remarkable in the context of everything else we've discussed. The moon's very dangers, the ones we've been carefully detailing across these last several parts, are precisely what make it such a powerful proving ground. Learning to manage lunar radiation, lunar dust, lunar temperature extremes, and lunar resource extraction in an environment where Earth is only 3 days away by spacecraft and a little over a second away by radio, that is far more forgiving a classroom than the 8-month transit to Mars, with Earth growing smaller in the rearview mirror every single day. If you're going to try building life support systems from locally sourced materials, learning on the moon while help is relatively close makes a great deal more sense than learning on Mars where help is months away. If your water extraction technology fails on the moon, you can potentially be resupplied from Earth in days. If it fails on Mars, you are in a situation of a fundamentally different kind. The moon's proximity is both its psychological comfort and its strategic advantage. Even though And this is the paradox at the heart of everything. The moon's surface environment is in several measurable ways more immediately deadly than Mars's, closer and more dangerous, farther and more forgiving. The solar system is full of these kinds of counterintuitive truths, and they are endlessly fascinating. But there's one more thing about the moon that we haven't touched on yet, something that reaches back much farther than Artemis, farther even than Apollo, and connects to the very deepest questions about where we came from and why the Earth is the way it is. The moon didn't always exist. It formed in one of the most violent events in the history of the solar system, a collision so catastrophic, so total, that it reshaped both worlds involved and set in motion a chain of consequences that ultimately made complex life on Earth possible. The moon is not just our nearest neighbor. In a profound and scientifically supported sense, it is the reason we are here at all. And understanding that, really sitting with what that means, changes the way you think about everything else we've been discussing. Let's go back, way back, not decades, not centuries, not even millions of years. We're going back 4.5 billion years to a solar system so young it would be unrecognizable to us today. A solar system still in the process of assembling itself, still chaotic, still violent in ways that dwarf anything we've experienced in recorded human history. The sun has just ignited. Around it, a vast disk of gas and dust is slowly coalescing, clumping together under gravity, colliding, merging, building. Rocky bodies called planetesimals are forming and growing, sweeping up material from their orbital paths, crashing into each other with energies that generate enough heat to melt rock. The inner solar system is a demolition derby on a planetary scale. Impacts are not rare catastrophic exceptions. They are the rule. They are how planets are made. And in the middle of all of this, a young planet, our Earth, is taking shape. It's already grown to most of its final size. It has a molten surface, oceans of liquid rock, a dense iron core, beginning to form as the heaviest elements sink toward the center. It's a world, recognizable in its broad outlines as the thing that will eventually become home, but utterly alien in its details. Now, sharing a similar orbital path around the young sun, slightly smaller than Earth, there is another planetary body. Scientists call it Theia, named after a titan of Greek mythology, the mother of the moon goddess Selene. Theia is roughly the size of Mars. It has been growing alongside Earth, their gravitational relationship gradually destabilizing until finally the inevitable happens. Theia hits Earth, not a glancing blow, not a distant near miss. A direct oblique collision, a strike so massive, so energetic, so total in its consequences that calling it an impact feels inadequate. The entire outer layers of both worlds are vaporized. Rock is turned to plasma. A vast cloud of debris, molten rock, vaporized silicate, shattered fragments of two proto-planets is thrown into orbit around what remains of Earth. The collision is so violent that it essentially merges the two bodies together, with most of Theia's mass absorbed into the newly reformed Earth and a portion of the ejected debris remaining in orbit. That orbiting debris, over a timescale that scientists estimate at anywhere from decades to perhaps a few thousand years, extraordinarily fast by geological standards, begins to reassemble under its own gravity. It cools, it compacts, it rounds, and it becomes the moon. This is the giant impact hypothesis, first formally proposed in the 1980s by planetary scientists William Hartmann and Donald Davis, and now supported by a substantial body of evidence including the analysis of lunar rocks brought back by the Apollo missions. The composition of those rocks, their isotopic ratios, their chemical signatures, matches Earth's mantle material with striking precision, far more closely than you'd expect if the moon had simply formed independently or been captured from elsewhere in the solar system. The moon, in the most literal sense, is made of Earth. But here's where the story stops being just ancient history and becomes something deeply personally relevant to you, because that collision didn't just create the moon, it set in motion a chain of consequences that quietly shaped every aspect of the Earth you live on today. Start with Earth's axial tilt. Currently, as we mentioned earlier, Earth tilts at roughly 23.5 degrees relative to its orbital plane around the Sun. This tilt gives us our seasons, the reason the Northern Hemisphere experiences summer when it's tilted toward the Sun and winter when it's tilted away. Seasons, in turn, drive the great climatic cycles that have shaped the evolution of life on Earth for hundreds of millions of years. The migration of species, the growth and retreat of glaciers, the cycling of nutrients through ecosystems, all of it is downstream in one way or another from the fact that Earth has an axial tilt. But here's what most people don't realize. Earth's axial tilt has not always been stable. Computer simulations of the solar system run without the moon in the models show that Earth's tilt would have been chaotic over geological timescales, swinging wildly between near zero and potentially over 80 degrees over millions of years. A planet tilted 80 degrees essentially rolls on its side. Its poles experience permanent sunlight for half a year and permanent darkness for the other half. Its climate becomes drastically, violently unstable. The kind of life that took hundreds of millions of years of slow evolutionary refinement to develop on Earth might never have had the stable, predictable environmental conditions needed to gain its foothold in the first place. The moon stabilizes Earth's tilt. The gravitational influence of our large nearby moon acts as a gyroscopic anchor, keeping Earth's axial tilt within a relatively narrow range over geological timescales. Stable enough for seasons to be predictable, stable enough for ecosystems to persist, stable enough for evolution to proceed along consistent lines over vast sweeps of time. Without the moon, there may well have been no stable Earth, and without a stable Earth, there may well have been no us. The moon's influence doesn't stop there. Think about the tides. The moon's gravity pulls on Earth's oceans, and to a much smaller extent, on Earth's solid crust itself, creating the tidal bulge that sweeps around the planet as Earth rotates. The sun also contributes to Earth's tides, but the moon's effect is roughly 2.5 times stronger, despite the sun being enormously more massive, simply because the moon is so much closer. Tides have done something extraordinary over geological time. They have been slowly transferring angular momentum from Earth's rotation to the moon's orbit, causing Earth's rotation to gradually slow down and the moon to gradually spiral away from Earth. 4 billion years ago, when the moon first formed, it was perhaps 10 times closer to Earth than it is today. Earth rotated much faster. A day may have been only about 6 hours long. The moon was enormous in the ancient sky, raising monstrous tides that swept around the planet with every short rotation. Over billions of years, as those tidal forces transferred energy from Earth's spin to the moon's orbit, Earth's rotation slowed and the moon moved farther away. Today, the moon recedes from Earth at a rate of about 3.8 centimeters per year, a fact we know with extraordinary precision because Apollo astronauts left retroreflectors on the lunar surface that Earth-based laser ranging experiments have been bouncing laser pulses off of for decades. But here's what makes this relevant to the story of life on Earth. There's compelling scientific evidence that the tidal mixing driven by the moon played a critical role in the chemistry of the early oceans, stirring nutrients, cycling minerals, creating the kind of rich, energetic coastal and tidal environments where many scientists believe the earliest life may have taken its first tentative steps. Tidal pools, sheltered, periodically exposed pockets of seawater, are still among the most productive and chemically diverse environments on Earth, and they have been proposed as one of the most plausible settings for the origin of life. The moon didn't just stabilize Earth's climate. It may have helped stir the primordial soup. There's more. Earth's core generates the magnetic field, shields the surface from solar wind and cosmic radiation. The generation of that magnetic field depends on the churning of liquid iron in Earth's outer core, a process driven partly by the heat of radioactive decay and partly by the energy released as the inner core slowly solidifies. Some scientists have proposed that the giant impact that created the Moon also played a role in structuring Earth's interior in ways that affect the long-term strength and persistence of the magnetic field. Though this remains an active area of research and debate, what is not debated is that Earth's magnetic field is unusually strong and long-lived compared to its neighboring planets. Mars lost its global magnetic field roughly 4 billion years ago, likely because its smaller core cooled and solidified too quickly. Venus, roughly Earth's size, rotates so slowly that its interior dynamics generate only a negligible magnetic field. Earth's field has persisted for billions of years, shielding life from the radiation that stripped Mars of its thick early atmosphere and scoured its surface. The Moon is woven into Earth's story at every level. Now let's let this land personally, because the science here leads somewhere that should genuinely take your breath away. Every atom in your body has a history. The carbon in your DNA was forged in the nuclear furnaces of ancient stars that exploded before our solar system existed. The iron in your blood comes from stellar deaths, supernovae so powerful they forged heavy elements that no ordinary stellar fusion process can produce. Your calcium, your phosphorus, your oxygen, all of it is stardust scattered across space by the violence of cosmic events billions of years old. But the specific configuration of atoms that makes you, a conscious, thinking, wondering human being, exists because of a sequence of events that includes the formation of the Moon. Without the giant impact, Earth might have had no Moon. Without the Moon, Earth's tilt might have been chaotic. Without a stable tilt, complex life might never have developed. Without complex life, there would be no nervous system capable of producing consciousness. Without consciousness, no one would be here to look up at the Moon and wonder about any of this. You exist in part because a Mars-sized planet crashed into the young Earth 4.5 billion years ago and created the Moon. Feel that for a moment. The Moon is not just our nearest neighbor. It is not just a target for exploration or a source of resources or a proving ground for deep space technology. It is a fundamental part of the story of life on Earth. It is older than the oceans. It is older than the continents in their current form. It has watched from the sky as life crawled out of the sea, as dinosaurs ruled the continents and perished, as small mammals crept out of the shadows and eventually stood upright and looked up at the night sky and began to ask questions. The same Moon that will bombard you with radiation and freeze you with temperature swings and fill your lungs with razor-sharp dust. That Moon is also the reason your ancestors survived long enough to become you. This is the paradox at the heart of our relationship with the Moon. It is simultaneously our most dangerous nearby destination and our closest cosmic companion. The world most likely to kill us if we step onto it unprepared, and the world most responsible for creating the conditions under which we exist at all. And now we're going back. Artemis II, the first crewed mission to travel beyond Earth's magnetosphere since Apollo 17 in 1972, carried 4 astronauts: Reed Wiseman, Victor Glover, Christina Koch, and Canadian astronaut Jeremy Hansen. They flew around the Moon and returned to Earth, the furthest any human beings had traveled from our planet in over half a century. Future Artemis missions aim to land astronauts at the lunar South Pole, near those permanently shadowed craters full of water ice. For the first time in history, the stakes of that return mission, understood in the full context of everything we've discussed, are staggering, because we are not just going back to plant flags and collect rocks. We are going back to learn how to survive. how to extract resources from an alien world, how to protect human bodies from radiation and dust and temperature extremes that have no analog in any environment on Earth, how to keep minds healthy and functional in conditions of isolation and confinement that exceed anything humanity has experienced before. We are going back to the moon because it is the hardest nearby school we have, and we need to graduate before we can take on what comes next. What comes next is a journey of 225 million kilometers to a world with a thin carbon dioxide atmosphere, iron oxide deserts, the largest volcano in the solar system, and canyons that make the Grand Canyon look like a crack in the sidewalk. What comes next is Mars. We're going to talk about what that journey actually looks like. Not the glossy mission graphics or the optimistic timelines, the real thing, the transit itself, 8 months in a spacecraft the size of a modest apartment with 6 people, watching the radiation counters tick upward every single day, the entry into the Martian atmosphere, which is simultaneously too thick to ignore and too thin to rely on, the first moments on the surface of another planet, and the question that every Mars mission planner eventually has to confront. How do you get people back? Let's make the crossing. Imagine you're strapped into a seat aboard a spacecraft the size of a modest apartment. Around you, 5 other people, your entire world for the next 8 months. Behind you, growing smaller with every passing hour, Earth, that vivid blue marble that the Apollo astronauts described with such reverence, the planet that made you, the planet your body was built for, ahead of you, nothing visible yet, just stars, just the deep, humbling blackness of interplanetary space, and somewhere out there, 225 million kilometers away on average, a rust-colored dot that you will not be able to see with the naked eye for weeks. This is what a Mars mission actually looks like, not the sleek cinematic version, the real version. 8 months of confinement, 8 months of recycled air and recycled water, and carefully rationed food. 8 months of the radiation counter on the instrument panel ticking upward, day after day, as galactic cosmic rays and solar particle events accumulate in your body's tissues. 8 months of communication delays growing from minutes to tens of minutes, Earth's voice becoming slower to answer, more distant, more like a letter than a conversation. 8 months of your bones losing density and your muscles losing mass, and your cardiovascular system quietly, gradually forgetting what it feels like to work against gravity. And then after all of that, you arrive. The entry into the Martian atmosphere is one of the most technically demanding maneuvers in all of spaceflight. A problem engineers call the 7 minutes of terror, which is the time it takes for a spacecraft to decelerate from interplanetary cruise velocity to a safe landing on the Martian surface. 7 minutes during which the spacecraft is surrounded by superheated plasma from atmospheric friction, communications are blacked out, and every system has to work perfectly without any possibility of human intervention from Earth. By the time mission control on Earth even knows the entry sequence has begun, it's already over. The spacecraft has either landed successfully or it hasn't. The atmosphere of Mars is thin enough that it provides only modest deceleration, nowhere near enough to slow a large, crewed spacecraft to landing speed on its own. But it's thick enough that you can't simply ignore it. You have to use it carefully, precisely, in combination with retrorockets and possibly large parachutes, in a choreographed sequence that has to execute flawlessly after 8 months of interplanetary travel, with hardware that has been shaken by launch vibrations and cooked by solar radiation and never once tested in the actual Martian environment. Getting people to the surface of Mars safely is one of the hardest engineering problems our species has ever attempted to solve. NASA's robotic landers and rovers have done it. The Curiosity rover, weighing about 900 kilograms, used a spectacular sky crane system to lower itself to the surface on cables from a hovering rocket-powered descent stage. The Perseverance rover, similar in size, used the same system, but a crude Mars spacecraft with life support returned propellant, food, water, and equipment for a stay of potentially 500 days or more on the surface would be orders of magnitude heavier. The sky crane approach, elegant as it is, doesn't scale to that kind of mass. SpaceX's Starship, designed to land on Mars propulsively, using rocket engines to decelerate all the way to the surface without parachutes or sky cranes, is the most ambitious current attempt to solve this problem. Whether it can deliver on that promise at the scale required for human missions remains to be demonstrated. But the engineering work is real, the testing is real, and the seriousness of the effort is not in question. Let's say you land. Successfully, the hatches hold, the habitat inflates, the solar panels or nuclear power system comes online. You step outside, or rather you go through the careful, methodical process of donning a Mars surface suit, running through checklist after checklist, and then stepping through an airlock onto the surface of another planet. What do you see? A sky that is not black, not blue, but a pale butterscotch color, pinkish tan at the horizon, shifting to a muted blue around the sun, dust particles in the thin atmosphere scattering light in ways that are subtly but unmistakably alien, a landscape of iron oxide, red rock and sand, stretching to a horizon that feels slightly closer than Earth's because Mars is a smaller planet, mountains in the distance that might be larger than anything on Earth. Olympus Mons, the largest volcano in the solar system, rises 22 kilometers above the surrounding plain, nearly 2.5 times the height of Mount Everest. A valley system called Valles Marineris stretches nearly 4,000 kilometers from end to end, long enough to span the entire continental United States. The gravity pulls at you at about 38% of what you feel on Earth. Not weightless, but noticeably lighter. You could jump higher than on Earth, though your suit and equipment would largely offset that. The air pressure outside is less than 1% of Earth's, utterly unsurvivable without a suit, but also, paradoxically, providing that thin atmospheric buffer that makes the radiation environment meaningfully less brutal than the open lunar surface. The temperature at the Martian equator at midday might reach a relatively comfortable 15 or even 20 degrees Celsius, briefly in direct sunlight. But by nightfall, it crashes to negative 70 degrees Celsius or below, and at the poles, it drops to negative 125 degrees Celsius in winter. The average surface temperature across the entire planet is about negative 60 degrees Celsius, cold, relentlessly cold, but manageable with adequate insulation and heating in ways that the Moon's 300-degree temperature swings between sunlit and shadowed surfaces present in an even more extreme form. The dust storms are a real operational concern. A global dust storm could reduce solar power generation for weeks to months, demanding robust backup power systems, likely nuclear, in the form of small fission reactors or radioisotope thermoelectric generators. The perchlorates in the Martian soil require careful management to prevent contamination of food, water, and breathing air. And, of course, the radiation, while less severe on the surface than on the open Moon, still accumulates over a 500-day surface, stay to levels that push hard against the career dose limits currently used for astronauts. None of it is easy, none of it is safe by the standards of everyday life on Earth. Every single day on Mars requires technology, discipline, and vigilance that have no parallel in human history. And yet the data, the radiation measurements, the atmospheric modeling, the dust chemistry, the gravity calculations, the psychological research on isolation and distance, all of it converges on the same conclusion we've been building toward through every part of this video. Mars is survivable in a way that the Moon, for long-duration human presence, is not quite, not yet, not with the technology we currently have. The Moon will kill you faster, in more ways, with less warning. Its radiation environment is rawer. Its temperature swings are more extreme. Its dust is more medically dangerous and more mechanically destructive. Its gravity is barely a whisper of what the human body needs. And if something goes catastrophically wrong on the lunar surface, a suit breach, a habitat failure, a cascade of system errors, the nearest help is 3 days away by spacecraft. Even if the decision to send that help can be made in seconds over a radio link, Mars gives you more atmosphere, more gravity, more radiation shielding from the planet itself, and a surface environment that, while deeply alien and demanding, offers more of the raw materials needed to sustain life over the long term. It is farther away, more isolated, and more demanding of human ingenuity and resilience. But the planet itself is a more forgiving host. Here's the way to think about it. The Moon is a test. Mars is the exam. The Moon is where we learn, in the most unforgiving classroom in the solar system, how to keep people alive in deep space, how to manage radiation, how to deal with dust, how to extract resources from alien soil, how to maintain psychological health in conditions of extreme isolation and confinement, how to build habitats, life support systems, and power generation capabilities that don't depend on regular resupply from Earth. We learn all of that on the Moon while Earth is still visible in the sky and a rescue mission is measured in days rather than years. And then, armed with everything that hard-won experience has taught us, we go to Mars, not because Mars is easy, but because of all the destinations in the inner solar system. Mars offers the most realistic long-term home for human civilization beyond Earth. It has days roughly the same length as Earth's, 24 hours and 37 minutes. It has a thin but real atmosphere that could in principle be thickened over geological timescales through a process called terraforming, though that remains firmly in the realm of the distant future. It has water ice at its poles and potentially in the subsurface. It has enough gravity to potentially sustain bone density and cardiovascular health at levels meaningfully above what the Moon offers, though still below Earth's ideal. It has a day-night cycle recognizable to human biology. Mars is not Earth, it never will be. But of everything we've found in the solar system so far, it is the world most amenable to the long, patient, enormously difficult project of becoming a place where human beings can not just survive, but eventually thrive. And here is the thing that I want to leave you with. The thing that ties all of this together. We started this video with a deceptively simple question. Why would the Moon kill you before Mars ever could? And the answer, as we've explored it, turned out to be far more interesting than the question. The Moon's dangers are real, and in many ways more immediate than Mars's. But the Moon's importance to the story of humanity, past and future, is also extraordinary in ways that go far beyond the simple question of which world is more survivable. The Moon was born in catastrophe and gave Earth stability. It stirred the ancient oceans and helped enable the conditions for life. It has watched over every moment of human history from the beginning, pulling the tides, lighting the night, inspiring every culture on Earth to look up and wonder. It gave us a target for one of the greatest technological achievements in human history, the Apollo program, and it is now, in the 21st century, giving us a target again, a school, a proving ground, a stepping stone, and beyond the Moon, Mars waits. Farther, colder, more isolated, but in its own way more inviting, a world with enough atmosphere to provide some shelter, enough gravity to load the skeleton, enough resources in the soil and ice to potentially support a civilization. A world where if we do the work, if we solve the problems, if we build the technology and develop the medicine and design the habitats and cultivate the psychological resilience, if we do all of that, human beings could one day stand on the surface and look up at a pale blue dot in the Martian sky, a dot that is Earth, and feel for the first time in history that we are truly no longer confined to one world. That is not science fiction. It is science in progress. It is happening right now, in laboratories and launch pads and research stations and mission planning rooms, carried forward by thousands of scientists, engineers, astronauts, and dreamers who have looked at the universe and decided that the appropriate response to its immensity is not fear but curiosity, not retreat but exploration. You are living at the beginning of that story. The moon wants to kill you. Mars is a little more patient about it. But the universe, vast, ancient, indifferent, and breathtakingly beautiful, is out there, and we are going.